Okay, so let's begin. Does anybody have any questions? Except what will be the paper in today's quiz? Anything else? I'm a bit surprised. I've still not hit full attendance till now, despite the quiz looming over you. Anyway, no questions. Wow.
So I had a question.
Go ahead.
So in the assignment, there was a terminology named as the maximum, like a safe forward current, as in
Mhm.
voltage.
Mhm.
So at that point, like the graphs we drew, like for
Mhm.
the ID versus VD.
Mhm.
So what changes, like how what would be observed? Like we see a peak, like for any current we would get, like for at that voltage there would be any current accepted, but then what would happen to the diode? Like it would simply burn out.
Well, actually, that's a good question. The way in which semiconductor devices respond to temperature is very critical. In fact, it's later on when we talk about many design issues, especially how amplifiers, etc., are designed, we will find that this particular point has to be given special attention. The basic idea, remember, is this. Okay, I'm going to draw a crude picture of the diode. As we have already explained, I am pretty sure all of you know this, and this is also in the videos, that you don't really make it out by joining a p-type and an n-type semiconductor together. There would be way too many gaps in the interface between the two in order that this would to make this function. So you grow a n-type region inside a p-type region and so on. But what exactly distinguishes an extrinsic semiconductor like the n-type one from an intrinsic semiconductor? Well, in intrinsic, you have electrons and holes formation primarily by bond breaking. So you basically have bonds which break into electrons and holes, and they also recombine. The electrons and holes recombine to form bonds. So this is really a reversible reaction. And that is the reason why you find concentration of n times concentration of p is actually a constant, or rather, it's a constant which depends on the temperature. So it's really a constant given the temperature is fixed. Now, this particular process, bonds breaking to produce electrons and holes, actually keep on happening, even in an extrinsic semiconductor, right? It's not as if in an extrinsic semiconductor suddenly you have
Yes, sir.
so only electrons and no holes, no bond breaking takes place. But you have to realize one thing, that suppose I have an n-type semiconductor, you have many more electrons and holes. And what is very important is that the number of electrons, of course, exceeds the number of electrons in a corresponding intrinsic semiconductor at the same temperature. But what about the number of holes? So n is much bigger than n0. Where by n0, I'm just denoting the number of, or consideration really, concentration of electrons at the same temperature in an intrinsic semiconductor. But what about the holes? How are they related to P? How is P related to P0? Yes?
P should be far less than P0 in that case.
Why?
Uh, so because since the electrons are very like in a bunch, so like more than n naught, so after
Hmm.
recombination there would be very less number of holes left, right? So it should be very less compared to P naught in that case.
Well, you're correct. And actually, this is basically what in chemistry is called Le Chatelier's principle, or basically the idea that if you have more of a product of a reaction, or one product of a reaction, it actually forces the reaction in the other way. More bond combination takes place because there are more electrons. So less holes are created. Okay, so this is what happens in between extrinsic and intrinsic thing. But as temperature goes up, what happens? This intrinsic uh, creation, which happens even in extrinsic semiconductors, is just that it's suppressed typically, becomes much larger because the more temperature you have, a larger fraction of the objects will have enough energy to overcome the so-called activation barrier and break the bond. So basically, there's an exponential increase in the number of these electrons, thermal electrons and holes. So now what happens is this. Electrons and holes, when they're created by thermal excitation, they're created in equal amounts, right? Each bond breaking creates one electron, one hole. Now, when the temperature rises a lot, and because of the fact that bond breaking increases exponentially fast with temperature, a stage comes when the electrons and holes essentially become almost equal. The initial advantage which you had, because there were donor ions which were giving more electrons, that's almost washed out. And the same happens on the p side. So basically what happens once the temperature rises a lot is that the junction between the p and the n, which is never really as sharp as we draw in the first place, simply gets washed away. And you end up with a single piece of semiconductor, not a junction, and then there's a sudden rush of current. Now, what might typically happen there is that your system may simply burn out, which is true. Even if it doesn't burn out, it will cease to function as a diode. Or it will function in a way which will be very, very detrimental to the way your circuit works. Okay. Usually, when people rate something as a safe current, there is always a margin of error. It means, suppose somebody says 1 ampere is a safe current through this diode, it doesn't really mean that it's going to burn up when you said 1 ampere. Okay? It actually means that it can really withstand more than 1 ampere, but just to be on the safe side, don't give it more than 1 ampere. Almost always these ratings which are made are done on the conservative side. You try to be safe. So if you think that your diode can take say 4 amperes, you code only 1. Now the reason why I say think is this. How do you know that a diode will take 4 amperes? You can't give a diode for current until it just burns up, right? You can, of course, but then the diode is gone, right? You can't use it any further. So what you do is you create a bunch of diodes. You don't really make one diode. You create a huge number of diodes by the same procedure. Take away a random sample from that. Carry out these characterizations, including checking when they burn out on that sample. Take the average value for that, and then if you find that in your sample diodes are typically burning out at a mean value of around 4 amperes, then you quote it as one. Quote the safe value as around 1 ampere. So if you ask what will happen if you just exceeded the safe current, your diode may still survive. But it's better not to try that. It might not, because remember, even though the mean in the sample actually burned out at 4 amperes, there are lots of fluctuations in your procedure. And unless you are paying a huge amount for very highly precise production levels, your given diode might very well burn up even at less than 1 ampere. So you don't even want to try to go close to that. Okay? So the real process usually is the breakdown of the junction, which destroys the diode for all practical purposes. Whether it burns up literally or not, that depends. That may not happen.
So, sir, before the burn up happens, so there would be like a upsurge of current through the diode, right? Since
yeah,
if
suddenly
bonds
the
are being
junction will
formed,
go
then
away
at
and
high
you,
temperatures bond may also
yeah,
break.
yeah, right.
So
Well,
so it would then go reverse reaction and again form the N and P pairs.
well, usually if you have a current, remember that statement, this bond breaking and recombination, this is an equilibrium situation. If you have a voltage which is driving a current through the circuit, the charge carriers may be swept out too fast for them to recombine. This recombination, this Le Chatelier principle of concentration of N on into concentration of P is a constant or temperature dependent constant. This thing is an equilibrium statement. When you are allowing currents to flow, then the electrons may not stick around. Right? So the statement that if you have many more N's, you will have much less P's, that actually works provided the N's are there to recombine. If there's a current which drags the N's along and out of the vicinity of P's, there will be no recombination. So the actual flow of current through a semiconductor under various conditions is really a rather fascinating and complicated story. We have not touched even the surface of that in these lectures simply because you have not studied enough quantum mechanics or London's matter physics and non-equilibrium statistical mechanics to really go into that. So what we are doing is we are giving a sort of picture of what's happening, which is more or less perfect, more or less accurate, I wouldn't say perfect, but more or less qualitatively correct. Okay. So the actual theory of flow in semiconductors is very, very complicated, and in advanced condensed matter physics, you do study a lot of that because it's also very important. Minute details of the behavior of a semiconductor device very often depends on these issues. We are in no position to discuss that in this class. Okay.
Okay, sir.
Okay. Now, any more questions? Oh, since we are on this topic, let me just put point out two things. One, in many of the circuits that I have given you in assignments so far, you have seen that the resistors are say 1 ohms, 2 ohms, 5 ohms, those kind of numbers. Okay. However, and hence of course typically because your voltage sources would be of the order of volts, the currents that you found out from your calculation were of the order of amperes. Okay. Now, this is actually way, way too high for electronics, in most electronics circuits. There are, of course, special circuits called power circuits, which do have currents which are of this order, but typical electronic circuit carries currents of the milliampere order. That doesn't mean that it is 1 milliampere, it could be 10 milliamps, but 1 ampere is a huge, huge current. Okay. And typical resistance, so this is a typical current. Typical voltage in an electronic circuit is of the order of volts. Again, I am quoting typical values. There will be circuits which handle hundreds of volts, or there will also be circuits which will handle millivolts or something of that kind. But your run-of-the-mill typical electronic circuits carry voltages of the order of volts, and the typical resistance is a kilo ohm or a mega ohm. By the way, the standard modern notation is K and M, and you don't really write the ohm after that. By the way, this is the resistance for resistance. What is the unit for conductance?
Mo or like ohm
Okay, that's
inverse.
written like this is called mho, which is of course OHM spelled in reverse. However, this by the way is rather cute and looks nice, but this is really not the modern SI unit. What is the SI unit called?
Siemens.
Yeah, it's called Siemens, which happens to be exactly equal. 1 Siemens is exactly equal to 1 mho. But the modern SI name is Siemens and it's written S. What is the typical conductance in an electronic circuit then? What's the order? That should be obvious from what I have said right now. I'm not asking you for information which you don't have.
Around 1 kilo Siemens.
1 kilo Siemens. Anybody with a difference of opinion there?
Milli or
Millisiemens.
micro?
Yeah, it's
Milli or micro.
Milli or
millisiemens or
micro.
microsiemens, not kilosiemens. Remember, when you're taking the reciprocal, kilo becomes milli. Kilo is 10 to the 3. By the way, this is something which is a bit of my own idiosyncrasy, you can say that. But if in your final workings or in your exam, I see somebody write, say, you want to divide a volt by a kilo ohm, 2 volts by, say, 5 kilo ohms, where I see somebody do this, so 0.4 into 10 to the minus 3 amperes, hence 0.4 milliamperes. If somebody does this, well, I'm not saying that I will deduct marks for that, but it will be very hard for me not to deduct marks for that. Because you have to realize that volts divided by kilo ohms is milliampere is actually more important for an electronic circuit than volt divided by ohms is an ampere. Okay? And volt divided by mega ohms is a microampere. These two things should be automatic. You shouldn't need to go through powers of 10 to get there. Okay. If you have to calculate it this way, which many of you do, I guess now, that just shows that you're not familiar enough with the convention, with the actual units that you will be using. In electronics, typical ratios are always kilo ohms and mega ohms and not ohms. Ohms, well, even if it's ohms, it's usually 200, 300 ohms. Not always. There will be special situations where you'll have 1 ohm or even less than an ohm in your circuit, but that's very, very rare. Okay, I'm talking of typical values here. And because of this, whenever you are working in electronics, these two relations, volt by kilo ohm is milliampere and volt by mega ohm is microampere. This has to be something which is drilled in your minds. You shouldn't have to work out powers of 10 to get to that answer. Okay? Of course, that might take some getting used to. And frankly, I have also been guilty of giving you circuits. Okay, in my defense, they were just for practice primarily to get you acquainted with the notion where you had these. Okay, so any questions on that? By the way, how much is a millisiemens into what would you typically multiply a Siemens with? Admittance multiplies what?
Volts, voltage,
Hmm?
voltage,
Voltage?
Voltage, right? So if you have millisiemens times a volt, how much is that?
milliamps.
That's milliamps. These are again things, I'm just stressing this because they may seem obvious, but very often people waste a lot of time trying to figure out the right power of 10 in such cases. And of course, you also need to be aware of this. Everybody knows this, but still, microampere into mega ohm is a volt, milliampere into kilo ohms is a volt, and microampere into a kilo ohms is millivolt. These are again trivial things, but very often one problem which physics students have, especially those with a theoretical bent of mind, is that you may handle formulas rather well, but when you are asked to put in actual numbers and find out real life results, very often that sort of becomes a problem, especially if you're not familiar with the numbers. You may end up by making, say, if you're multiplying, you just by mistake might divide and end up with an outlandish result. The trouble is you may not realize that that's an outlandish result, okay, unless you're a bit familiar with the numbers. And that actually goes for all branches of physics, not just electronics, of course. Being familiar with the typical numbers that you would encounter in a branch of physics is very, very important. If not the precise values. So I don't expect you to memorize the charge of an electron to say 8 decimal places. But you should all know that it's 1.6 into 10 to the minus 19 coulombs. Okay? So that kind of knowledge of numbers is very, very handy. And without that, frankly, if you know a lot of equations, that doesn't really help you much in real physics situations. Okay, that was one point I wanted to make. The other point I wanted to make is this. In continuation with the question that was asked a while ago, the point I would like to make is temperature and heating are very, very important issues in electronics. In fact, as I said, many of the design of circuits that you're going to see, much of the thought process which goes behind designs is in handling this issue. So, for example, how many of you have seen a transistor? I don't mean a transistor radio, of course, I mean a transistor. Anybody? Of course, if Akhil, is that a dot, or I'm not very sure whether that's a current lingo for something. Okay. Some people are saying they have. Of course, if you had a lab, you would have definitely seen a transistor by now. So that's just rubbing it in a bit. But unfortunately, I don't have a transistor right in front of me. But typical size of transistor, can anybody tell me the transistor that you have seen? How big is that? How much is it from one end to another? Roughly the linear dimension in centimeters, let's say. Would it be a few millimeters or a few centimeters? Half a centimeter. That's sort of okay. Now this is really not one size fits all. Transistors come in all shapes and sizes. So do diodes. A typical diode that you would find in a lab is roughly this big. I'm drawing a real life scenario. This is what the diode would typically look like, but you could have diodes which are much, much larger. But this half a centimeter around, those are the kind of transistors that you would see in labs. You would have something like a. So does this sort of look like the kind of transistor that you have seen? Okay, you must ignore my drawing skills, which are horrible, but still. Okay, so good. Now, next question. You all know that transistor is a PNP device, right? Or an NPN device. So there's some semiconductor here. So where exactly is the semiconductor? That is the silicon chip which contains M, P, and N. In this whole thing, where is it? So I will give you choices. Is it here? Inside? Of course, this whole thing is metal, but inside. So is the transistor here in this cap? Where is it? The actual transistor, the semiconductor piece. Okay. Well, okay, let me give you the answer. You may not, of course, know. If you are, okay, I'm not sure how many of you have actually handled the transistor in your hands. Again, sorry, if you are great in the lab, you would have. And if you are in the lab, you would typically get a chance to also examine transistors which have got blown out for whatever reason. Maybe you drove a huge amount of current through it and destroyed it. And once you have supplies of that, one of the natural things which you should really try to do is take the thing apart and see what's inside. It takes a bit of effort, but if you open up this cap, any guesses what you will see inside the cap? If you could pry this open, and what would you see here? Any guesses about what would you see here? I'm asking you to guess. Of course, unless you already know, you would have to guess. So let's just say I've managed to cut this thing and opened up the cap. What would you see? Come on, I'm asking you to guess, so you can just be outlandish and say whatever you want.
We see that NPN type like.
Okay, you see the NPN. That's what might seem to be an obvious thing. Actually, what you see is nothing. It's air. Inside, there is nothing. It's just a hollow cap. So where is the semiconductor? Now guess. I'm talking about typical transistor design. Well, actually, if you carried through the work a bit more, you would find that this flat cap actually is not a flat cap. Yeah, people have said in the base, at base, near the wires, that's actually correct. But if you were to pry open the flat cap, that actually is two metal plates stuck very close to each other. And in between those two flat caps, there's a very, very tiny thing. You'll find a very tiny brownish piece, which is in between these two. So there are actually two plates here. It's very difficult to figure out that there are two plates. It looks like one solid piece, but in between these two plates, there is actually this actual semiconductor. So the real question is, if the semiconductor is really that big, or rather that small, then why do you have all this? Why do you have the caps? I can understand why you have three legs. You need to connect them to external circuits. But why have a rather large cap?
To maybe keep it protected from like the dust or anything.
Okay, but for that, the two plates would have done. You're right. One job of the cap is to keep it protected from external environment. In fact, it's very difficult to pry the plates open simply because it's sealed very, very tight. Okay, Shivam has actually given the right answer. Although the answer right now was also partially correct. The real reason why you have a cap is the cap actually gives you higher surface area. It's a metal piece, it has big surface area. So what does it do? It actually drives heat away from the thing. Okay. Whenever a semiconductor is used, current flows through it and it heats up. And it heats up rather drastically. It would have heated up rather drastically. The metal plate that you have, the cap, all of this is just an attempt to give it more surface area to radiate the heat out. So it's called a heat sink. The cap itself is a heat sink. Now, in fact, if anybody has opened up an old television set, for example, not the newer fancy ones, I don't recommend opening them up at all. And by the way, I don't even recommend opening up the older sets unless you're sure that the power is off. Those that have huge voltages might kill you, in fact. But you would find something like which looks like this, in fact, even bigger. Something with size is something like this. A diamond-shaped thing with a round thing sitting in there. That diamond-shaped thing with the round-shaped thing is also a transistor. It's a power transistor, something which carries a lot of power. And there also, the actual transistor is really this big. This huge thing, the much bigger thing is really there to provide a much bigger surface area. And why? What? How does it help? It helps by allowing heat to flow away. In fact, in old television sets, you will find this thing sort of connected to a big piece of metal, which has shapes like this. Okay, my apologies for this horrible drawing, but anyway, it has teeth like this, and this is what it looks like. Any idea why do you need to put in so many teeth? What do the teeth do? Okay, teeth may not be the right word for it, but it's like
It
sort of
increases the surface area.
exactly. It's a solid piece of metal. If you cut it up, every time you cut it, you get extra area, and extra area is there to drive heat away. This is very, very important because heating is really a huge enemy as far as semiconductor circuits are concerned, and you want the circuit to be cooled as far as possible. And then you have to ensure that your circuit actually does not respond too badly to heating. That will be, as I keep on saying, that will be a major concern in when we design our circuits. And bear this in mind, because later on when we talk about thermal stability and all that, this is going to be a very important issue. Okay. But I do suggest one thing. If you get hold of a transistor which has burnt out, okay, be a bit careful. It might be a bit dangerous to try to prying it open with anything. But if you're careful enough, you should be able to pry it open and see this. This is one of those situations where I'm not saying do not try this at home. I'm actually asking you to try this at home. Please just don't go ahead plucking out actual working transistors from your family radio set and do the experiment. Of course, this is going to destroy the thing. But if you get access to something which has burnt out already, and you will have plenty of such access when you come to the lab, because burning out things in lab is essentially how people learn, then you should be able to sort of do it for yourself and check that what I'm saying is really true. Why do they use air as the heat sink? If that is the case, why do we? Well, actually, they do that. So when you say air as the heat sink, you mean why is there air inside? That's not used as a heat sink. I'm sorry if I give you that impression. It's really hollow inside. The hollow thing is simply there so that you can use a lot of metal to give a large area. The same amount of metal, if it had been solid, would have had a much smaller area. It's hollowed out. The cap is hollowed out simply so that you can get a much bigger area. Area, of course, is useful because it helps you to radiate away the heat. Okay. Air, of course, is a bad conductor of heat. It's not the air which conducts. This whole thing, remember, this is metal, this is metal, this whole thing is metal. So you are allowing the heat to flow through the metal and then radiate away. Of course, you could have kept it solid metal inside, but that would have increased the cost. So it's a balance. Remember, electronics is after all about real devices which you make. So cost is very important. You don't put in metal where you don't need metal. On the other hand, actual heat sinks like this, which are actually called heat sinks as separate entities, they are made of metal. But even there, you have these pieces taken away. And that serves two purposes. One, it allows you to use less of the metal, which is going to be expensive. The other is it gives you more surface area. And by the way, this is not all, because say in your laptops and other things, there is way too little space to have this kind of transistors. You have integrated circuits, and there also heating will become a huge issue. And so one of the most important components in your laptop happens to be a thermal paste. It's not a component, but it's basically a gel-like thing which is there underneath the top layer, which does not short out the thing. It's also designed rather carefully so that it doesn't short out the electrical current flowing, but it can carry the heat away. And one of the reasons why many laptops malfunction is because of heating. That's the reason why you cannot make a very tiny laptop, because after all, you at least need to put a fan in there. to cool the thing down. The fan, of course, circulates the air around and allows the heat to flow away. Okay. Any other question? Okay, it seems that there are no other questions. Yes. Fine. I didn't really expect many in today's class. Everybody is eagerly waiting for the exam, it seems. Okay, so let me just tell you a bit about the exam. So in electronics, resistors are used almost everywhere. How is power consumption dealt here? You have to live with power consumption. You can't do much. Of course, if you have resistors, you have to ensure that the resistors don't heat up too much. The problem is when resistors heat up, it doesn't really happen with resistors. But if you have other electronic components too much in the vicinity, then those will heat up, especially semiconductor devices will heat up, and that will be a problem. There are clever ways of reducing power dissipation in resistors, but depends. It's not always what you would want, right? But the important thing is in your, say, even within a transistor, okay, I'm getting a bit ahead of the story here because we have not talked about transistor construction yet. But can anybody tell me this? You have already done this in class 12, I guess. This picture of the transistor, NPN, 3 equal blocks. This is of course false because you don't really create 3 pieces and put them together. But are the relative sizes even correct? Do you put in 3 equal blocks?
No, sir.
No, sir.
So can you give me a relative idea about the sizes? Which one is smallest? Which one is next? So you have the emitter, the base, and the collector, right? You all know this. So which one is the smallest of them, or at least thinnest of the 3?
Base.
Okay, base is the thinnest. There is a very good reason for that. So we will come to that when we talk about transistor action. But among the emitter and the collector, emitter is very strongly doped, collector is lightly doped. Sizes.
The collector is larger than emitter.
Why?
To reduce because collector surface behaves as a heat dissipating surface.
Well, the reason why it has to do that is collector and emitter carry almost the same amount of current, but the collector is lightly doped, so it's much more resistive. So it produces much more power, much more heat. And in order to take away the heat, the collector has to be larger. First of all, that gives it a bigger mass, so bigger specific heat. So temperature rise for the same amount of heating is less. More importantly, it gives it bigger surface area. And also this, well, I did say that there is a semiconductor piece which in the middle of the plates, but it's the collector which is in touch with this plate. So the collector actually is in thermal contact with the plate, and the plate takes away the heat from the collector. Okay. Fine. So these are very important issues in actual construction, and they all have their reasons. They're not just there to sort of just because somebody suddenly thought, let's make the base thinner. Okay. Right. Any further questions?
Sir, what do you mean by thermal contact with the plate?
Thermal contact simply means contact where heat can flow. Okay. That's it. So the emitter really is not in contact with the metal, because if the emitter and collector had both been in contact with the same metal plate, then they would have just shorted out. There would be no voltage difference between them. So now let's talk about the thing that everybody is interested in, and that's why I have such a huge attendance today. The quiz, okay. That will be 30 minutes. 4 MCQ questions. I'm not saying everybody will get different questions, but people will get different questions. And more importantly, this 30-minute is absolute. Okay, 30 minutes for 4 MCQ questions, of course, seems quite a lot, right? Because you typically get 10 minutes for 4 MCQ questions in most exams. But this is because these questions have to be worked out. And this is important. In your quiz link, you will answer the questions. That is just A, B, C, D. Just click on the link. Okay? But you will also have to work out the thing alongside. Anyway, you will have to. Without the working out, you will not be able to get those answers anyway. I don't need these worked out things to be very neat or precise or anything, but I do need enough in each of these questions to see whether you have worked it out. Okay. So the working out, you will have to scan your work, that is whatever paper or anything you work on, and upload that in the system within 10 minutes of the quiz ending. So there will be 2 links, one for the quiz, another for the upload of your scanned work. So you have a total of 40 minutes to upload the scanned work after you finish the quiz. The important thing is your marks will depend on what you did in the quiz itself. So which buttons you click. But unless the scanned work is there and unless it corroborates that, you are not going to get credit. So if you claim that the problem was so easy that you could work it out in your head, sorry. I haven't been able to work those questions out in my head. They're not very difficult questions, but I haven't been able to work them out in my head. And I'm not going to assume that somebody among you can. You may be a genius, you may be able to do it, but I'm not going to believe you. Okay, so show your working. But once again, if you work out the whole thing in that scanned sheet and you haven't submitted the answers in your quiz, you get 0. You get marks only for the answers submitted in the quiz, but those marks will be validated by looking at the scan sheets. Is that clear? Any questions? So you get 10 minutes from the end of the quiz for this. Okay. So if you have any questions, ask now. And by the way, if you say frequency there in either the question or the answer, and it has a 1 by 2 pi in it, is the actual frequency. If it does not have the 1 by 2 pi in the formula, then it's the angular frequency. Or rather, what is it called? I keep on confusing it. Yeah, without the 1 by 2 pi, it's omega. With the 1 by 2 pi, it's actually f. Can you give 5 minutes more to submit? You mean 15 more minutes? Okay, I will change the setting. I hope I will remember to change the setting. Anything else? None. Okay, so the next announcement, you can all log out. Okay, let's do it a bit later. But you can all log out from GMeet because this quiz is not on GMeet. This quiz is actually on WeLearn. So to log into WeLearn, the quiz will be available at 10 a.m. till 10:30 a.m. And as of now, we will see 10:40 being the deadline for the upload of the scan sheet, but I'm going to change that to 10:45. Okay, so this will become 10:45 then. Okay? Any questions? None. Okay, so bye for now. I'm giving you 10 minutes time to get ready and everything. At 10 o'clock, you will have the quiz. And this will continue until 10:30 for the, by the way, there is no grace time for the quiz. Whatever you answer within 10:30, you are going to get scores for that. You will not, if you manage not to submit by 10:30, whatever you have answered till 10:30 will automatically be taken. There will be no grace time for that at all. And there will be no grace time beyond 10:45 for the upload. If you don't upload, you get 0. Any questions? None. Good. So let's call it a day. That's for me, not for you. You still have first the exam to give. If you raise your hand, you better speak. Tell me.
Sorry, sir. I raised it by mistake.
Okay. Okay, then bye for now.